A modern cruise ship sailing through the tropics represents an astonishing feat of engineering, a floating city designed to provide luxury in environments where the sun beats down relentlessly. Yet, a walk out onto the upper decks on a sea day reveals a bizarre reality. Despite the massive size of the vessel, thousands of passengers are forced to share a statistically minuscule body of water. Why don't the naval architects simply utilize the vast open space on the top deck to build larger, more adequate pools? To understand the engineering hurdle, we have to look at the volume required. A standard Olympic-sized swimming pool holds 2.5 million liters of water, creating a concentrated mass of 2,500 tons. These pools represent an absolute boundary dictated by physics, structural limits, and corporate economics. Understanding this phenomenon requires stripping away the luxury veneer to examine the structural cost of static weight, the mathematical limits of ship stability, and the deadly dynamics of liquid mass. Fresh water is incredibly heavy, and bunkering it from shoreside connections is a significant commercial expense. Strict sanitation requirements, specifically the response to a Code Brown contamination, force ships to maintain massive internal reserve tanks just to replace the volume of a single pool. This cross-section shows the weight gradient used in modern shipbuilding. The superstructure requires significantly less strength the higher you go because there is less ship above it to support. Dropping a 2,500-ton pool onto the uppermost deck places an immense static load on the weakest part of the ship's frame. To support this mass, architects would have to add thousands of tons of heavy structural steel, driving pillars all the way down to the keel to carry the weight. Every vessel has a finite maximum weight capacity for buoyancy. This creates a zero-sum game between the weight of construction materials and the ship's payload. The added mass of the structural steel and the water directly cannibalizes the weight capacity meant for fee-paying passengers. Placing immense static mass at the highest point of the ship destroys its commercial viability by replacing revenue-generating payload with non-profitable deadweight. Beyond total weight, the specific vertical location of that mass creates a far more dangerous problem for the vessel's safety. Maritime stability is a continuous balancing act between two opposing physical forces. Gravity pulls downward through the center of gravity, the mathematical average position of all mass within the ship. Buoyancy pushes upward through the center of buoyancy, the geometric center of the underwater hull. When wind or waves force the ship to lean or list, the underwater shape of the hull changes. This causes the center of buoyancy to shift outward toward the deeper, submerged side of the hull. The horizontal separation between the downward pull of gravity and the upward push of buoyancy creates a lever, a righting moment that naturally twists the ship back upright. Placing thousands of tons of water on the top deck changes everything. It drags the ship's entire center of mass upward. With an artificially high center of gravity, the horizontal distance between these two forces all but disappears when the ship leans. This neutralizes the ship's natural righting lever, transforming a stable vessel into a sluggish object prone to rolling over. Solid mass remains fixed, but liquid reacts to motion. This reaction is known as the free surface effect, and it is exponentially more dangerous than a static load. As the ship leans, gravity forces liquid in the pool to rush outward, forming a massive, heavy wedge on the lowest side of the vessel. This relocated mass physically drags the ship's entire center of gravity horizontally off the centerline. The shifted weight forces the ship to list further, causing even more water to rush outward, which drags the center of gravity even closer to the waterline. Unpartitioned liquid movement is a primary cause of major maritime disasters. The catastrophic capsizing of roll-on roll-off ferries like the Herald of Free Enterprise was caused by this exact phenomenon, wide, shifting bodies of water destroying the ship's stability in minutes. A massive, wide pool on the top deck of a cruise ship recreates these same dynamic vulnerabilities at the worst possible height. If a cruise line demanded a massive top deck pool, an architect would have to find a way to mathematically counter these forces. The solution is to pack the bottom of the hull with ultra-dense ballast to forcefully drag the center of gravity back down. Placing thousands of tons of permanent ballast in the hull requires stripping out massive amounts of usable interior volume. Ballast is deadweight that generates zero revenue, permanently reducing the total carrying capacity of the ship. Sacrificing thousands of tons of fee-paying payload just to counteract the physics of a large pool is an absolute non-starter from a business perspective. Because cruise lines cannot afford deadweight ballast, architects solve the problem by changing the geometry of the pool. Restricting the width of the pool physically breaks the leverage of the free surface effect. When the ship leans, the liquid has very little distance to travel, keeping the dynamic wedge of weight trapped safely near the centerline. However, even a long, narrow pool still contains an immense total volume of water, keeping the static load too high for the superstructure. The modern solution is to utilize very small, low-volume plunge pools designed to trick the eye. Designers surround a tiny, deep section with expansive, ankle-deep weighting perimeters to create a large visual footprint. These wide ledges provide space for passengers without adding significant mass, ensuring that any shifted wedge of water during a roll is mathematically negligible. When a cruise ship requires a genuinely deep pool for acrobatics or scuba training, the placement must change entirely. These deep pools are nested at the stern of the ship, as low to the waterline as structurally possible to protect the center of gravity. The cramped pool on the Lido deck is an engineering compromise, balancing the limits of fluid dynamics and stability against the economics of ship payload.